Welcome back to G4 Lab IBCS. In this video, we'll be continuing our discussion of Topic 4, Computational Thinking, Problem Solving, and Programming. In our last two videos, we covered computational thinking and program design, including pseudocode, flowcharts, and trace tables. This video, we will cover standard algorithms. So to remind you guys about the rubric, this is the IB Computer Science syllabus, and we are on Topic 4. And if you need a catch-up on computational thinking, things like pseudocode, flowcharts, and trace tables, and problem solving skills, go check that out. Okay, so standard algorithms basically is IB's umbrella term for these four algorithms. That includes sequential search, binary search, bubble sort, and selection sort. We'll be going over this in detail in the later slides. So it's important to note you'll be expected to write these both in pseudocode and scratch that. Not in code. You might be required to code it, but if you would like, you could use code like Java or Python, but IB notations pseudocode is completely acceptable, and if you need a refresher on how pseudocode works, go check out the last video. You'll be expected to trace them and modify them, like adapting for descending order and swapping count. So any algorithm outside of these four is not to be expected to be memorized on the exam, but they will be given to you or broken down enough for you to work them out. So if it's not these four, you can work them out, but you're not expected to memorize them. Okay, so the first one's sequential search. This is the easiest one to understand. So the purpose of sequential search is to iterate through a set of data one by one until you find the item you're looking for. So here we have a list of some letters, 23 letters, right? You start from 0. Okay, so our goal is to find J. J is right here, right? So iterating through, you start from 0. The program starts from 0, checks if the J is at A or is at 0, checks is J equal to A? No, it's not. Moves on to B, checks, check, check, all the way to 9. And J is right here. So there, that it'll return 9 as the number where you found J. So note, sequential search does not require your data to be sorted to work. So this is sorted right now, but if it was like B, A, C, E, F, X, Y, Z, whatever, it still works because it doesn't matter where letter J is. It'll just iterate through. Okay, here's a pseudocode for sequential search. We'll be using the example of a needle in a haystack, and it doesn't matter what the actual values for the haystack and needle are. It could be, the needle could be J, and the haystack could be all the letters in the alphabet. It doesn't matter. So we're just going to abstract that away. So for I to 0 to length, I to 0 to length, haystack, I want to do -1. Because remember, for example, right here, there's the actual length of this is 24, right? It's 24 letters. So if you do length of this data, that'll be 24, but you want to do from 0 to 23 because we're not using the normal counting system. This is programming. We start counting at 0. So always remember to include -1. So if haystack is I equals needle, then return I. So this is basically saying if we find our needle at I, then we want to return the value of I. Then we want to say end if, and for return -1. Why is it -1? Because that just returns a negative. It just ends the program and it tells you that it's saying that the needle does not exist. And then at the very end, end function. Okay. So if the loop finishes and the element was never found, it will return -1. The reason it's -1 because -1 is not a valid index in a way. So it only goes up from 0 to length -1. So -1 is used as the value to indicate that the element does not exist. In terms of efficiency, this one would be, since the element is beginning at the list, which only takes one comparison, and it's giving a complexity of big O of 1. But the worst case occurs when the element is at the very end. So it could be, let's say J was at 23. That would require you to check every single element. So the worst case scenario is big O of n. So how many data arrays, it could be like 50, 1,000, 10 million. It would be big O of n, sorry. Okay, moving on. I'm going to talk about binary search. So a binary search divides a list into 2 halves and continues to divide it until the desired value is found. So this one's a little bit tricky. So first of all, the binary search requires your data to be sorted beforehand. right? It's not like sequential where you can have any combination of letters. It has to be sorted. So here we have a sorted list, same as last time. So, and we still want to find j. 23, where is, we want to find the middle of 23. We want to divide it into 2 halves. So that will be 11, which is L, right? Divided in half, and the program will first search if j is in this right half, right? And it's not, so it discards it away. So we're not going to worry about this anymore. And then now we're going to repeat this process. Now there's only 11. It goes from 0 to 11, right? Middle of that is number 5, right? Number 5, check left, check right. Left, no j, discard. And then do the same thing. Half from 5 to 10, half of that will be on number 8, discard the half that doesn't have j. And now, look, now we try to divide from 8 to 10, and we land right on j. So every time we divide it in half, we have to first check the value that we land on. Is that value the value that we want, right? Is f going to be L? No, it's not. So discard the half that doesn't have. So eventually we land on j. So this is known as iterative binary search. There's also a recursive version, but we'll look at it in a later unit. So just be aware that if you were to Google binary search, there are 2 types, so you want to be careful. Okay, pseudocode. Okay, binary search and pseudocode. Function binary search. Array. We're just going to be using array target for us. Just be boring. Okay, so low 0, high length array. We're just setting the boundaries. Minimum is 0, maximum is the length minus 1, right? Okay. Say while low is smaller than or equal to high. I want to find the median. So low plus high divided by 2, right? High divided by 2. If array mid is equal to the target, this is where we're checking if the target that we land on when we divide it in half is the target, right? If the place we land on is the target, then return mid. So that's our best case, is we divide it in half and we just land on it. Else if array mid is smaller than the target, then we want to do low is equal to mid plus 1, right? So if this middle value is smaller than the target, then we're setting a new minimum from mid plus 1. So we're ignoring the side that we don't want, right? Like for example here, see? If it's lower than the value, half of 11, 5, right? It's lower than that value, then our new minimum will be from plus 1, 6 to 10, right? Otherwise, I want to do high. This is the other case. What if it's on the right side, then we want to set the maximum to the middle plus 9 minus 1, right? Kind of visualize that. Okay. And if okay. And then we want to get outside of the loop, and then we do end while return -1, and then end function, right? Okay. Now we're going on to bubble sort. So this is where it gets kind of weird. Bubble sort, I want to remind you that this is sorting now. We're not doing searching anymore. We're taking, sorting is taking a non-sorted, scattered, 1932, blah, blah, blah. We want to do it into ascending or descending order, right? So for this example, we're going to be doing ascending order, right? Bubble sort is a sorting algorithm that sequentially goes through the list of values and swaps adjacent values until a sorted list is created. Okay, so here, this is every step written out, right? We want, starting from 19, remember, it goes sequentially, so it starts from 0, goes all the way to the end. Is 19 bigger than 32? No, it's smaller, right? So this is sorted, so it leaves this. Then it sets the new, and then we start checking at 32 again, right? We move on to 19 because that's perfect as it is. 32, 11. Which one is smaller? 11. Switch 32 and 11. Okay, and then you want to move on to 32 and 21. Which one's smaller? 21. Switch, swap, 21, 23. So now it becomes 19, 11, 21, 32. Do the same thing all the way to the end, right? you can see it takes a couple tries because at the very end of the first pass through, it might take more than one, by the way. On the first pass through, the first value in your data in your list and the last value will always be the minimum and the maximum. So these two will be set. As you can see, the biggest value in this list is 42, right? And then at the end of the first iteration, 42 is at the very end and 19 is at the front. And then you want to go second pass through if it's needed, right? Going back through, it's 1911, right? 11's smaller, swap. 19, 21, perfect. 21, 32, perfect. 32, 14, not perfect. 14, switch with 32, all the way to the end. See, this can be very tedious, but all the way to the end, then we got it sorted, okay? So in a nutshell, we're starting at the beginning of the list. We're comparing each pair of neighbors. If the left is greater than the right, then you want to swap. After one full pass, the largest element is at the very end. That's what I was talking about. First pass, largest element is at the very end. Repeat for the remaining unsorted parts. Stop when no swaps occur, the list is sorted, or all passes are completed. Right, so we have the same list as in bubble sort. We're still starting at the first value, but now whatever in the unsorted part of the list, so all of these numbers, you sequentially compare 19 to each of these values until you find the smallest value out of all of these that's also smaller than the first number of 19. And then if it's smaller than 19, like 11 here, then you swap, right? See, this is every single step. You're comparing 32, 11, that's got to hit. So, but you don't swap until you've compared the whole list. Because what if there was like a 9 in here? You don't know until the program doesn't know until it iterates through. So if there was a 9 in here, it might be at the very end. So even if this 11 is smaller than 19, it still has to go through the rest of the list. 32, 11, 21, 39, 14, 42, and 25. Then it goes through, right? 11 is smaller than 19. Swap. And then you're moving on, right? So I is no longer than at 0. We're doing I plus 1. So I is at 1 now. We're starting at 32. Compare 19. Oh, it's smaller than 32. But there might be more, right? 21. Nope. 39. 14. See, 14 is smaller than both 19 and 32. But you wouldn't know if you didn't iterate all the way through. And then going all the way to the end, 14 is the smallest, and it's smaller than 32, right? Do this. Keep going until you have a completely sorted list. In a nutshell, start at index 0. Find the smallest element in the entire list. Swap it with the first element. Move to index 1. Find the smallest element in the remaining list. Repeat until the list is sorted. So I think the pseudocode for this one is probably like the most straightforward one. Right, for every value in the array. For every value to the right, want to compare current value to right value. Okay. If a right value is smaller than the current value, then save index location of the right value. And if and for if an index location was saved, then swap current value and right value, and then you want to do end if. Same thing as always, end if, end for. You're just ending the if statement, and the loop right here. Return array. And always remember set for the last one. Okay, that's it for this class. Thank you for watching. Next class will be concluding the rest of topic 4. So we just have some algorithm efficiency and programming concepts to go through, and then we'll be all done for topic 4. Thank you.